wanted to show you guys how I coded this neural network. It's a feed-forward neural network, so it's a pretty simple one. The idea is that I'm trying to make a quantum decoder. So in order to decode errors, we need to have, in order to decode errors, we need to have errors in the first place. So this is the noise model that creates the errors in a vector. So basically, we're just going to take this long string of numbers, some zeros, ones, twos, and threes, and just going to scramble them up. So these are just a random number generator. And if you look here, the 1 would correspond to an error in the x direction. 2 corresponds to an error in the y direction, which is a combination of x and z. And then the 3 is just a z error, so we just get a z error. So the idea is we're mixing errors in the x direction, errors in the z direction, and if you see, this would map to just an error in the x, this would map to an error in the z, this maps to an error in both, and etc. So here's the probabilities that we would even get an error. Um, Basically, there's a 94% chance of getting an identity, which is no error. This is just an example. We could put a 2% for 2% and a 2% so that there was about a 6% chance of error. And this is kind of a way to generate some probabilities. So this is a noise model that essentially we're going to be trying to decode. We want to get these error vectors. So yeah, that's the decoding task. We need to get this 4x4 surface code, which is this HZ thing. It's this gigantic matrix. And we have an HX, which is like a 7x16, and an HC, which is an 8x16. The idea is that these H matrices are just zeros and ones. This is just 0 and 1s, nothing crazy. But these are going to manage the syndrome checks. And a syndrome check is basically this calculation method. We're going to take the H and we're going to multiply it by the transpose of the error vector, and we're going to take a mod 2. We'll try to explain what that means. The idea is if the H says there's a 1, then it wants to check that particular qubit. So you can see that we have some 1s and we have some 0s here, and we're going to basically be either checking these, so it moves into this line here where this S vector says, okay, I'm checking S1, or no, um, this is a sum of all of the syndrome vectors. So this is one syndrome vector here, as you can see, and then we could take all the 1, 2, 3, 4, 5, 6, 7, and 16. We can put them all into one here. And so each one of the syndromes is going to be doing, okay, we're going to check this qubit, we're going to check this qubit, we're not going to check this one, we're not going to check this one, we are going to check these two. And then what we're going to do for the mod 2 is we're calculating whether it's an even or an odd number of errors. And that's it. And then if it's even, then that particular row will show up as a 0. If it's odd, it will show up as a 1 over here. So it's a pretty simple way of keeping track of how many errors are in a system. So the idea is the decoder is going to try to predict EX and EZ, which was these things, EX and EZ. We're going to try to figure out exactly which EX and EZ it is based on this input right here. And it's kind of hard because there's degeneracy here, where one syndrome vector here can create many different EXs and EZs, so it can become a pretty difficult task. So that's why we want to get a little feed-forward neural network. Now, this is not the best way to decode this, but it's one way. It can decode some very simple errors, like one error happening in the vector, maybe two, if it gets really, really lucky. And I might be able to show a demonstration of it later. We'll see how that works. Um, so we've got 5 layers in the network that I built. Input bits, it's going to be this. So you're just going to input some bits, which is zeros and ones. It's the S vector I was talking about. And then what we're going to do is we're going to basically pose a little linear transformation. We're going to scramble up these numbers a bit, and we're going to sort of make a little pattern with just real numbers here. So these are called logits. These are bits, and these are logits. So you can see there's just real numbers. There's positive numbers, there's decimals, there's negative numbers. And this is a huge vector of 1,024 entries, whereas the syndrome vector was only 15. So we can make a huge vector here. Then we're going to do a ReLU activation. This is just a special function that's going to pull out only the positive numbers. So we're cutting out the negatives. We're still at 1,000 entries. So the next one, we're going to do another linear transformation here. And so we're going to re-scramble the numbers again. So we get all this, and we got some negative numbers again. And then we're going to do another ReLU, so we're going to cut out the negatives, boom. And then we're going to output the logic. So we have to convert this back to bits. Oh no, sorry, that happens a little later. But we're going to output those logics here. And we're going to output them in this way that we sort of divide the entries into 32 parts. There's going to be, instead of 1024, we're going to put them back to 32. But anyway, this is going to give us EX in the first 16, EZ in the next 16. So then we can do a sigmoid. So the sigmoid is going to convert these numbers, these logits, to probabilities. So now we've got probabilities instead of random numbers. Just okay. And then from this, we're going to gauge this loss. So we're going to compare the probabilities here to the actual vector. And this is the actual error vector. And we're going to say, okay, we're going to give it a penalty score based on, you know, based on how close it was to this actual vector here. So like this would get a very low score because it's close to 0, right? Uh, this would get a high score because it's trying to predict a 1 in a place where there's a 0. So that would get a large penalty. All right, and then the weights, we're just basically going to use those penalties and those losses. We're going to try to minimize that loss using the Atom Optimizer, and he's just going to basically go through and keep adjusting the weights so that every time we go through this process, we get a lesser and lesser loss penalty. And that's basically it. Then at the end, once we go through this training cycle hundreds of times, we basically try to make a little prediction, and it's going to kind of, like I said, predict if it's greater than 0.5 on the probabilities, then it will say it's 1. And if it's less than 0.5, it will say 0. So these will show up as zeros. This will show up as 1, 1, 1, and so we predicted this, even though this was the correct vector. So we get a little bit of a penalty. Anyway, so this is a pretty cool setup and a nice little neural network. A lot of fun. So let's see if we can maybe look at like some of this code, because I think the code is kind of cool. Here we have the H matrices that I was trying to show, just big zeros and one matrices. And then this is how we're sort of making the errors. You see, we're basically generating errors here, and we're converting them to EXs and EZs, and then we're trying to sort of compute the syndrome here, and then that's basically it for this little piece here. We could look at this model that I was saying was a 5-layer network. So you can see here's the first layer, second, the third, the fourth, and the fifth, and they're basically just doing little calculations. We're converting. I mean, also, this is just this one line right here. That's the code. This is just a whole bunch of comments, and this is it. This is the second line. This is the third line. So this very, very small amount of code. What's happening here? Okay, well, anyway, so here we go. This is like you can see, it's just this little piece right here. That's it. That's the fourth layer. And then this is the fifth layer. That's it. Very simple. And again, this is pulling out the two pieces into 1616. It's a pretty easy model. And then when we want to actually go and train, this is where maybe the fun might happen. Wonder if I could try to open this in a terminal. Well, while that's loading, we can go and take a look at this code here. So we have a lot of samples. Here we're assigning the probabilities, trying to pull the generate error function, and essentially just running all the stuff we need to run here at the beginning. And then we have this training size, so we're going to split that 500 samples, 5,000 into 4,000, and then we're going to later test it on 1,000. So we split that up right here. And then here we are calling the model. So here we're building the FNN. And I guess we're going to be putting weights in. So these are the weights. And from those weights, we have this criterion, that's the loss that we're sort of calculating. And then we have the optimizer that's going to sort of use the loss to update the weights. And then we've got 50 epochs. We're going to run this about 50 times. And see the optimizer run each time, scores and losses, blah, blah, blah. This is all just kind of printing the calculations out. And then later we're going to have this evaluation where we're going to sort of make a single error, but we're going to test the accuracies so that you can sort of see how good it was at predicting errors. Then we're going to try to test it with a single error by creating a random error and then seeing if Decoder can decode that error. So let's go ahead and see if it works now. Yeah, okay, cool. So what it's showing here are the two H matrices, this HX, HZ, and then we are using a 4x4 lattice. So yeah, and then basically these are the epochs. So we got 50 epochs about, and you can see how the loss starts pretty high, and it starts to decrease as the epochs run, and as the atom optimizer starts to shift those weights around, and this thing just keeps cycling over and over again, right? We're almost done here. I made a pretty short one. So you can see the loss gets down pretty low. But this is also just due because I have a very small chance of error. So there's only like a 2% chance of error. So we're only going to get one error appearing on the vector. So that way it actually works. Because if I start putting 2 or 3 errors into the regular neural network, this isn't a graph neural network. It's just a feed forward one. So it was able to predict this one properly. As you can see, we had one error, and it was able to predict it just fine. But on this one had 2 errors, and so it took a guess of zeros all the way across, and that was wrong. So we got one of the error vectors correct, but not the other one. Um, Although you can see in general we have a pretty high accuracy, but again, that's only because we usually only get one error. As you can see, as soon as we get 2 errors, we kind of don't get very good accurate results. Let's see if we can run it one more time and maybe we'll get some different vectors coming out of it. Unfortunately, it has to run through all 50 epochs, which is kind of lame, but that's in order to get the loss down so it actually predicts something properly. Then, well, if we were predicted with only 20 epochs, it wouldn't be very good. So we kind of need to get this loss function down to a small number. But yeah, that was pretty fun. Just running a little feed-forward neural network and seeing if we can predict quantum errors. So we're getting a 10 loss. See if we can get under 10. Probably not. So there we go. Well, this one was a pretty sad situation. We didn't get any errors, unfortunately, in our single error decoder. So this one didn't work out so well. We predicted 2 errors here, but that wasn't even good. So as you can see, it's very difficult to make this actually work because it's just a regular feed-forward neural network. Like it's not a graph neural network. It doesn't have a lot of capabilities. As soon as we get more than one error, it starts to be wrong. And the percentage error that I gave it was like 2%. So, it's just a very small chance of getting there.